Hey everybody, welcome to video 7-2. In this section, we're going to be talking about isosceles triangles and equilateral triangles. So I'm here on page 328, as you can see, and we're going to highlight one theorem, which is the isosceles triangle theorem. So make sure you put a star next to that or highlight whatever you're doing to keep track of those important pieces. It says if two sides of a triangle are congruent, then the two angles that are opposite those sides are congruent. This theorem is also sometimes called the base angles theorem, but usually we talk about the isosceles triangle theorem as its name. And so just a quick review of, remember, the vocabulary for an isosceles triangle, and this, if you skipped over it, is back on page 327. But if I have an isosceles triangle, then the two sides that are marked congruent might have tick marks, might have actual measures given. But what we're talking about here is that if we go across the triangles opposite them to the bottom corners, that we can also say that these angles, and go across this way as well, across the triangle to the bottom corner, that these angles are congruent. The vocabulary associated with these sides, you guys, is that these congruent sides are called legs, and then the side on the bottom is called a base. No surprise, the angles at either end of the base are called base angles. And the angle at the top between the two congruent legs is known as the vertex angle. Just some vocabulary to keep clear here. Okay, we're going to go over to the next page, page 329. And I don't want to go through all these proofs necessarily, but I do want to highlight the idea of the isosceles triangle theorem's converse. So if you look at step 2 right here, we have the converse of the isosceles triangle theorem. Remember what we started with in the isosceles triangle theorem was if the sides were congruent, then the angles were congruent. So a converse, remember, turns that conditional statement on its head and simply says, now my hypothesis is my conclusion, and vice versa. So I'm going to start this time knowing information about two angles of a triangle are congruent, then the two sides opposite those angles are also congruent. Okay, so again, just a quick summary. The isosceles triangle theorem starts with sides and makes a conclusion about angles. The converse of your isosceles triangle theorem starts with information about with the angles being congruent, and then the conclusion that you can make is about congruent sides. So just a quick little summary of those two. Now let's use them on page 330. Okay, now you guys, I'm on page 330, and we're moving on to equilateral triangles. Just like isosceles, they also have two theorems, one normal theorem and then the converse. So notice the information that we have here is still moving in the same direction. The theorem itself says if the sides are congruent, then the angles are congruent. That's the first one, or the words that they're using. If a triangle is equilateral, meaning all the sides are the same, then it is also equiangular, meaning all the angles are the same. And then notice a little further down the page, we focus on the converse, which starts with knowledge of the angles instead. So if the triangle is equiangular, then it is also equilateral. Let's go to the next page and start using these theorems with the isosceles and equilateral triangles. So I'm on page 331 now, and we have here example 3. It says Katie is stitching the center inlay onto a banner that she created to represent her new tutorial service. It's an equilateral triangle with the following dimensions in centimeters. We want to know what is the length of each side of the triangle. So the important piece of that is that it's equilateral, and so we know that all the sides can be marked the same. So we're going to substitute right here the two expressions, 6x minus 5, into the equation, and the two sides are equal, so it's going to be equal to 4x plus 7, and simply solve for x. Pretty straightforward. We get x equals 6, and then we want to know what is the length of each side, so we're going to substitute that 6 in for x, and get that each side is 6 times 6 minus 5, or 6 times 4 plus 7. We get 31 either way. A little further down the page, part B, we're going to look at not an equilateral triangle, but we can see from the markings here that we have an isosceles triangle. In part B, this time we're being asked to find the measure of angle T. So it says that's, of course, the vertex angle. To find the measure of the vertex angle of the triangle, first we're going to find the value of x. So we know from the isosceles triangle theorem that the measures of the base angles in an isosceles triangle are the same, or if we want to trace across again, we've got tick marks here and here, so that means the angles across from those tick marks have to also be marked or are also congruent. So if one is marked x degrees, then the other one is also marked x degrees. So when we add those three angles up, r plus s plus the measure of angle t, we know that has to be equal to 180 in the triangle sum theorem. So x plus 3x equals 180, or adding like terms, 5x equals 180, and dividing by 5 we get that x is 36. That's simply the division property of equality there. And so if we know x is 36, then the measure of angle t is 3 times that 36, or 108 degrees. See what you guys can do with the your turns numbers 5 and 6 at the top here of page 332, and we'll see you guys in the next video.